Okay, hi grade 12s. What we're going to look at today is one type of compound. We're going to look at our ionic aggregates, and we're going to start with what this term means, aggregates in overall, total. We're going to look at a definition of it, a little small calculation, and then you're going to have quite a bit of time to just work on one kind of particle, physical, chemical properties, and answer some questions. Okay? So we are covering pages 21 to 26 in this topic, and then tomorrow's lesson you'll be covering the molecular compounds. Okay, so what are we talking about when we use the term an aggregate? We're really talking about one type of substance. Okay, an aggregate therefore is a pure substance composed of identical particles that are held together by attractive intermolecular bonds. So if you will, I want you to think about one kind of particle all together in a container, because then if you're only talking about one thing like water, then water together has the exact same physical and chemical properties. It has the same melting point. It has the same boiling point. The force of attraction between the bonds of the water are the same throughout the substance, so we can group them together and then we can talk about the properties that they have. Okay, so whether I'm talking about a beaker filled with pure salt, which is sodium chloride, or pure copper metal, or pure water, or pure diamond. There are 4 different categories of aggregates, and in grade 12 we get to talk about 3 of the 4. Okay, so you're going to fill in this fill in the blank note, or make a summary note as best you can. If you didn't print the notes, that's just fine. And remember, we're talking about now the bonds between the particles of the same type that are in an aggregate. So these are the intermolecular bonds, and these are the ones that are very weak. They're the ones that break when something changes the physical state, right? Because water in the liquid state would look something like this. In the solid state, it would be grouped together, and then in the gaseous state, they'd be far apart. So we're going to talk about those bonds. All right, so highlight number 5, 6, and 7, those blanks, because those are the 4 groups of aggregates that we're going to be dealing with. So ionic aggregates, that's today. Molecular and metallic aggregates, that's tomorrow. And when you get to university, then you'll talk about the 4th group of aggregates. But these are things that I know you already know about. Diamond, okay? Covalent networks are the strongest group of compounds that we have, and those are the 4 different categories, okay? All right, on the bottom of this page right here, after you've filled those in and gone through, then let's check some calculations. Again, I know we already brought up Avogadro's number and what we're talking about, how many particles per mole. Here's where you're going to be specific, because we need to talk about which kind of particle we're talking about. Okay, so for example, sodium chloride, well, that's an ionic particle. So I could have 6.02 times 10 to the 23rd ionic particles per mole. Just see how we're adding that in as a specifier there, the kind of particle. So if I was looking at water, which is a covalent molecule, these are our molecular compounds, I could be talking about 6.02 times 10 to the 23rd waters, and then I would refer to them as covalent molecules. Okay, what if that particle type is an atom, like Fe? Well, then I could be talking about Avogadro's number of atoms per mole, or I could be talking about molecules per mole. So see how I'm looking at these different specifiers in my units. Okay, here's the calculation that you wanted to work through. Calculate the number of ionic particles that you have in a sample of 0.523 grams of zinc acetate. The question's already given you the molar mass, so you're halfway there, because again, that's a bit of review. So we know that you know how to calculate molar mass given 1 decimal place. How do we use that? Okay, so if you need to get to the number of particles, you start your unit analysis with the number that you were given. And in this case, it was 0.523 grams. That's my mass. I'm going to multiply that by my molar mass because I need to convert my grams into moles. Remember, the top unit would cancel out with the bottom unit. So if you just solved the first part, your answer unit would be moles of zinc carbonate. zinc acetate. And then the next part would be, I need to know how many particles, and we know Avogadro's number is 6.02 times 10 to the 23rd particles per mole, because this unit would cancel out with this unit, and my final answer would have a unit of so many particles. Okay, which kind of particles? Let's even specify that. It should be ionic particles. Same. Okay, this is a good question to practice if you're not sure how to use or remember how to use your significant digits, but your scientific notation, that's what I meant to say. Your scientific notation button on your calculator. Everybody's calculator is different, so make sure you know how to use it. Do I have the right number of significant digits though while we're talking about it? Let's double check. This measured value has 1, 2, 3 significant digits. You don't count a 0 that's before the decimal place or anything to the left. This value here has 4 significant digits. This value has 3 significant digits. When you're multiplying and dividing, your answer will have the same number of significant digits as the value that had the least number, which in this case is 3. My answer will have 3 significant digits. Okay, and for the last part there, what if it said, now, can you calculate the number of carbon atoms that are in that amount of zinc acetate? Yeah, you've got 1.72 times 10 to the 21 particles. I need to get it to carbon atoms. How many carbon atoms are there per particle? Can you count that up? How many carbon atoms are there per particle? 1, 2, 3, 4. There are 4 carbon atoms per particle, and my answer 6.87 times 10 to the 21 carbon atoms. And again, when you're using Avogadro's number, remember it's a measured value. I can have a mole of bunches of bananas. I can also figure out how many moles of bananas I have if each bunch has 7 bananas per bunch, right? It just depends on what you're talking about, and so you use your units to help navigate that. Okay. On the next page, page 21, you're going to read through, you're going to highlight. This is your summary of physical properties at the molecular level. Okay, you need to be able to explain these physical properties, and so because different aggregates have different physical properties based on the kind of aggregate they are, you can make a generalization about things like melting point and boiling point, volatility, hardness, solubility, and electrical conductivity. So I'll let you work away at that, highlight, add to the notes if you need to. All right, now here's where we go over our aggregates, and on the next few pages we're going to deal specifically with ionic. And remember, today is all about ionic aggregates. So we're talking about ionic particles, and there's our definition again of aggregates, and then let's go into our definition of ionic aggregates. And if you go through the notes, you can see the little header there where we're now starting right here at the top of page 23 with ionic aggregates. And again, make your own summary on ionic. If you don't have the course notes, that is just fine. Add to the details from the notes and from the lesson. Okay, all right, here we go. What are the particles that make up this aggregate? Well, if it's an ionic aggregate, it's made up of ionic particles. Okay, how do we recognize they are ionic? It's because there is a metal and a non-metal put together. What are some examples? Now go ahead and write some examples down. You don't have to use mine, use your own, but don't do easy ones, right? Do ones that are a little trickier. So you've got magnesium oxide, copper 2 sulfate, zinc acetate, iron 2 chloride, iron 3 chloride. Practice your nomenclature every time you do some of these examples. Don't just use mine. Okay, the intramolecular bond, what's inside this particle? How do you identify the IAM? If it's ionic, remember it's easy because there's only one kind of ionic bond, and it is called ionic. Easy. Ionic aggregates have ionic intramolecular bonds, and intermolecular bonds are also ionic. Remember, these are salts. They look like crystals. And so there are many different beautiful shapes of crystals, but these crystals are all formed between ionic particles. So you can't distinguish between which particle bond you're talking about. Are you talking about the intramolecular bond or the intermolecular bond? And again, they are the same. They are identical ionic bonds. So it's just how you reference them, okay? You'll be making reference to these types of bonds when you're describing a physical change and when you're describing a chemical change, okay? So just like if you're looking at a molecular compound, if you're talking a physical change, a change in state, you're talking about breaking the intermolecular bonds. And if you're talking about a chemical change where you have to break the inside bonds, that's an intramolecular bond, okay? So you're only going to use that when you're referencing the type of example that you're given. If it's a physical change, you're talking about the intermolecular bonds breaking. If it's a chemical change, you're talking about the intramolecular bonds. And we use these all the time, so please use the short form IAM for one between the particles. Can you see that? And then IEM when you're referring to within the particle. Again, it's ionic no matter which way you look at it. Okay? All right, now let's explain the physical properties. You've already done the summary page on the left there, or sorry, the one previous. And now you just want to look at what are some of these examples, okay? And how do you explain the physical property with what that physical property is and the reasoning. And again, you're explaining it at the molecular level. So see what you remember from grade 11. Put a little bit more work into this. If you didn't quite get there in grade 11 last year, you'll be able to pick it up no problem today. Okay? Remember, we're talking about metals and nonmetals. They have the same relatively the same physical properties within the group of ionic, and I'll show you what some of the differences are in a second. Melting point, boiling point. What are they? Relatively high. Can you give me some numbers? Well, you certainly know what the melting point and boiling points are of water, which is our molecular compounds. How much higher? Well, look, the boiling point of a salt, sodium chloride, is 1,413 degrees Celsius to boil salt. Boiling water, way lower, 100 degrees Celsius. Okay, remember what's happening at the molecular level? You say when something melts, some of the intermolecular bonds are broken. Okay, all at the boiling point. All of those intermolecular bonds are broken. So look at this wording specifically here. You did some of this already in the grade 11 review. We're reviewing it again, okay? We go over some of these important concepts again and again. There's solids at room temperature, right? Volatile, nope, they are not volatile. Salt that's sitting in a open container on your counter will be a solid 25 years from now, okay? Water sitting on your counter is not going to be water in the liquid state 25 years from now. In fact, it will change into a gas very quickly because, again, of its lower boiling point. Okay, whereas the high boiling point means that it will remain a solid and it will not sublime. All right, hardness, hard but brittle. There's your diagram there that shows that. Okay, can you show a diagram like that very specifically? I think there's one in the homework question, right? Have a look at those ions. Sodium 1+, chloride 1+. What happens? The like charges come together, like charges repel, and it shatters. Okay, so that's why it's hard yet brittle. Next, the next physical property, you're looking at water solubility. Again, we bring up what are the solubility rules. Okay, so yes, most of our ionic particles are water soluble. Not always, though. It depends on the polarity. It's also going to depend on the strength of the bonds that the particle has. Okay. Electrical conductivity, yeah, you know that even back from grade 9. Does it have ions? Is it mobile? So if it has ions and they're mobile, they're going to have moderate to good electrical conductivity. Okay, is it as good as a metallic aggregate? No, right? Because those are charged ions in a sea of electrons, and so we don't use salt to create our cords to power our house, right? But we certainly do use metal, and so as a group, our ionic particles have, yeah, moderate, fairly good electrical conductivity when they're in the liquid and aqueous state. As a solid, yeah, no, the particles are not mobile. Okay, all right, I'm going to leave this one here. This is a great explanation of dissolving water. There's a video that does it way better justice than what I can do just talking about this. But this, again, is one of the really important misconceptions or potential misconceptions in chemistry about dissolving, because remember, dissolving is a physical change. So what does that look like at the molecular level, and can you explain it? You sure can, right there. Can you write that in your own words though? Summarize that so that you understand and you've got that in your notes. You're making reference to intermolecular bonds, and you're talking about what those new bonds are forming called. Okay, so don't skip out on some of the terminology that's given here. All right, the last little bit is the one that is the extension. This is sort of new to grade 12. It's a concept we'll come back to a couple of times, but we recognize the fact that not all ionic particles are the same. They're not all sodium chloride. And so is there a difference when you're looking at physical properties like melting point and boiling point within the ionic aggregate group? And yes, there is. Okay, you can actually calculate the force of the bond within an ionic particle. That's going to be different based on two things. So I know this looks a little confusing, but I want you just to think about the two things that will create a stronger force for that bond. Okay, those two things are how far apart those ions are, so that's the radius, the distance between the center of one ion and the center of the other one, okay? And the difference in the charge of those ions. Those two things factored in together, you can actually just calculate what the force of the bond will be. And here's the interesting concept. Once you've calculated the force of a bond, then if that bond has a very strong force, it's going to be very hard to break it. Okay, so a strong bond is going to translate into a very high melting point, a high boiling point, and a low solubility. Strong bond, very hard to break, and so it translates into a high melting point, a high boiling point, and not very good solubility because the bond is strong. If you have a weaker ionic bond, it may be because the ions are a little bit bigger. Okay, what if they're farther apart? They're going to be weaker. What if the charge difference between those ions isn't, maybe no charge difference? Then you're going to have a weaker force. And then if you have an ionic particle with a weaker force, what you're going to do is it will take less energy to boil, less energy to melt, and it's going to have better solubility because of that weaker bond. Okay, so we're going to compare those to the charge of the particles and the radius, and then make some conclusions based on the force. Okay. Okay, so let's look at this table down below. There's a few things for you to fill in, and this is the summary table right here. If we're comparing sodium chloride and sodium chlorate, okay, can you see here that they both have a +1 charge and a -1 charge, a +1 charge and a -1 charge? So if you're comparing these two, the Q values will give you the same calculated value. The radius is what's different, okay? You can see here that the radius between these two ions is a lot smaller than the radius between these two ions, okay? When you put those values into a calculation, and again, you're not going to have to memorize this formula. I just want you to memorize these two trends, okay? The trend then, the force that you get between a sodium and chloride ion is going to be larger than the sodium chlorate. You're going to have a smaller force. Okay, so which one is going to have a melting point that's higher? Which one's going to have better solubility? Okay, so let's summarize that. Larger force, this one is going to have a higher melting point because of the larger force, and solubility, it is going to have lower solubility. It's not going to be as good because of that higher force, that larger force that holds them together. Okay. Conversely, if you were to compare two other ionic particles, sodium fluoride and calcium oxide, +1, -1, +2, -2, they have roughly the same radius. Can you see those values? 231 picometers, 239 picometers. They're roughly the same. But because of the bigger charge difference between them, this one is going to be higher, and so it will have a lower solubility if you're just comparing those two. Okay, I want you to summarize that in the corner of the note. Just make sure you've got those trends. And that's how you can look within that ionic aggregate as a group. There are some particles that have a greater strength of the bond versus others. We use the charge and the radius to help us figure that out. And then we use that information to explain the physical property of melting point, boiling points, and solubility. Okay, now you're going to work away at the questions on page 26, and we'll chit-chat about this maybe in the last learning block. If we have time, I'll open up the virtual classroom. Okay, good luck.